Welcome to the deep dive. Today, we're strapping in for an exploration into the world of aerospace technology.
Yeah, thinking about what really goes into those incredible machines that fly.
Exactly. What sparks the engineering that lets us cross continents or, even head out into space?
Well, we've looked at an interview with an aerospace technologist, someone right in the thick of it.
And we've distilled those insights. The idea is to give you a guided tour, sort of the key ideas behind designing, building, maintaining these, well, complex machines.
That's right. We know you want the real understanding, but maybe without getting bogged down in super technical jargon.
So our goal, our mission for this deep dive, is to pull out the most fascinating bits, the most crucial parts of this technologist's perspective. Think of it as a shortcut to understanding this really complex field.
A shortcut, yeah. Let's jump in.
Okay, so first up, what actually draws someone to aerospace? What's the spark?
Well, for the technologists we focused on, it started young, like a childhood fascination.
With planes,
Yeah.
space.
Both, really. The simple wonder of flight, but also that ambition, to reach for the stars.
But it wasn't just dreaming, was it?
No, it was about connecting that wonder with engineering precision, wanting to solve actual real-world problems.
In aviation, like everyday planes and space systems, too.
Exactly. That combination of aspiration and, well, practical engineering. The awe turns into a career focused on design, on solving tangible problems, turning dreams into reality through, really meticulous work.
Right. And speaking of meticulous work, let's talk about actually designing these things digitally.
CAD software, computer-aided design.
Yeah, forget the old drafting tables, right? Our technologists really stressed how vital tools like AutoCAD, CATIA, SolidWorks are.
Absolutely essential these days.
And they gave a great example,
Hmm.
using CATIA specifically to model reinforcements for aircraft wings.
Structural reinforcement?
The challenge being make the wings tougher, more durable against flight forces,
Yeah.
but, and this is the key part, without adding much weight.
Because weight is everything in aerospace.
Exactly. Every extra pound costs fuel.
Mm.
So figuring out that balance, strength without weight, that's a huge win.
It really is. And the precision you get with tools like SETA is, well, it's transformative. You can simulate stresses on a wing under all sorts of conditions down to a really fine level.
Before you even build anything physically.
Precisely. In the past, you'd need multiple physical prototypes, build them, test them, maybe even break them. Very costly, very time-consuming.
So CAD lets you test and optimize virtually, much faster, much cheaper.
And with incredible accuracy.
Okay, so you've got this perfectly designed wing in the computer. Now it actually has to, fly efficiently, slice through the
Like
air.
aerodynamics.
Right, that whole concept of drag, like sticking your hand out of a car window, that resistance.
That's it. Aerodynamic efficiency is all about minimizing that resistance for the aircraft.
And our experts said this massively impacts fuel use performance.
Huge impact. They actually worked on reducing drag for UAVs, drones.
Unmanned aerial vehicles, yeah.
And the goal was to extend their flight range. Less drag means they can fly further using the same amount of power. It's a tangible benefit.
Makes sense. Even small improvements must add up, right?
Yeah.
Especially for big airlines.
Oh, absolutely. A tiny percentage reduction in drag across a whole fleet. That can mean millions, literally millions, in fuel savings every year.
Wow. So it's a constant push for optimization.
Always. Pushing the limits of what's aerodynamically possible for better performance, lower costs.
But, even with the best designs, things can go wrong. Components malfunction.
It happens. These are complex systems.
So what's the process then? Our technologist described it as very methodical troubleshooting.
Systematic, yes. Like detective work.
First step, looking at the clues. Technical schematics, the detailed diagrams and diagnostic data from the aircraft itself.
What does the system say is wrong?
Then the physical inspection, actually looking at the component, followed by simulations, trying to recreate the problem in software.
And crucially, collaboration, talking to other engineers.
It really sounds like a team effort to pin down the issue.
It has to be. In aerospace, with safety being so critical, you need that systematic approach. Schematics give the theory, data gives real-time info, inspection finds hidden physical issues, simulations test hypotheses safely.
And different engineers bring different perspectives.
Exactly. It leads to a more robust solution.
Okay, so you've fixed a problem, or you have a new design. You can't just, hope it works in the sky, can you?
Definitely not. That's where testing comes in. Rigorous testing.
Our interviewee mentioned things like wind tunnel testing.
Yep. Putting a model, or sometimes even a full-scale component, in a controlled airflow to see how it behaves. Standard practice.
Also, vibration analysis, making sure things don't shake apart.
Right. And thermal stress testing, checking how components handle extreme temperatures, hot and cold cycles.
And get this, they mentioned environmental testing for satellite parts, making sure they survive launch and then the vacuum and temperature swings of space.
Orbit is brutal.
Sounds like it. Talk about a tough environment.
It is. These tests push components way beyond normal operating conditions. For satellites, maybe simulating years of space radiation to check for degradation.
So it's not just, does it work? It's, how close is it to breaking?
Pretty much. You need to know the limits and ensure a big safety margin.
And it doesn't stop after design and testing, does it? There's maintenance.
Constant maintenance. And the technologists often stay involved.
How so? Our expert mentioned working closely with the maintenance teams.
Yeah, analyzing recurring faults, problems that keep popping up.
And then feeding that back into design, suggesting changes to make repairs easier or prevent the fault in the first place.
Exactly. It shows how design choices impact the entire life cycle of the aircraft, improving reliability, improving safety, reducing maintenance time.
Design for maintainability. Makes sense.
It's critical. The maintenance crews see how things really perform over years of service. Their feedback is invaluable.
Okay, this field moves fast, right? Technology changes. How do people like our technologists stay current?
Continuous learning. It's absolutely essential.
What does that look like? Reading journals.
Definitely. Things like Aerospace America. Attending webinars, conferences the AIA, the American Institute of Aeronautics and Astronautics, hosts a lot.
Taking courses, too.
Yeah, short, focused courses on new things like composite material modeling or new propulsion system designs. Things are always evolving.
So you can't just learn it once and be done.
Not at all. New materials, new software, new scientific understanding, you have to keep up. It's not just nice to do, it's necessary to stay relevant and contribute effectively.
Let's zoom in on some key systems. Avionics, for instance.
Ah, the brains of the operation.
Basically, all the electronics, right?
Okay.
Navigation, communication, cockpit displays.
All of that. Managing flight control, monitoring systems. It's complex.
Our interviewee actually got hands-on with this during a university project.
Yeah.
Integrating GPS
Global positioning system.
and autopilot modules into late aircraft prototypes.
That kind of practical integration experience is gold. It's not just knowing what GPS does or what an autopilot does.
It's making them talk to each other reliably.
Precisely. Making all the different electronic systems work together seamlessly. Like conducting an orchestra, everything needs to be synchronized.
Of course, these big projects, they don't always go smoothly. Challenges pop up.
Always. Especially when you're pushing boundaries.
Our technologists shared one example, a drone design project. They ran into unexpected instability.
Ah, yes. In crosswinds, winds hitting it from the side.
And fixing it wasn't simple. It meant, well, kind of going back to the drawing board.
More wind tunnel testing to really understand the airflow. More computer simulations.
And then actually redesigning parts, like the tail configuration.
And the control logic, too. The software telling the drone how to react.
It's a great example of that troubleshooting and iteration process in action.
It really is. You design something, you test it, it reveals problems you didn't anticipate. So you analyze, learn, redesign, test again. That cycle is fundamental to engineering. Overcoming hurdles is part of the job.
Throughout all of this design, testing, fixing problems, there's one thing that's absolutely non-negotiable, isn't there?
Safety. Always safety first.
Our interviewee really hammered this home. Strict adherence to safety regulations, like from the FAA here in the U.S.
The Federal Aviation Administration, yeah. Or EASA in Europe.
European Union Aviation Safety Agency. And it's not just following rules, it's about thorough validation, proving a design meets all the safety requirements.
And meticulous documentation. Recording every decision, every modification, every test result.
So safety isn't just a final check, it's built in from the start.
It has to be. It's ingrained in the culture and the process.
Yeah.
The stakes are simply too high. Protecting lives is the absolute priority.
To help ensure that safety and just to optimize designs generally, simulation software seems incredibly important.
Oh, massively important. Saves so much time and money compared to purely physical testing.
Our technologists mentioned tools like MATLAB and Simulink for modeling systems.
Right. And things like X-plane for flight simulations, seeing how the whole aircraft might behave.
And NSYS Fluent. What's that for?
That's often used for computational fluid dynamics, or CFD, analyzing airflow over a wing, for example, visualizing it.
So you can test countless scenarios virtually before cutting any metal.
Exactly. You can explore different designs, different conditions, identify potential problems really early on, all in the computer, find high drag areas, potential turbulence, things you might miss
It's
otherwise.
like a virtual test flight.
In many ways, yes, it significantly reduces the amount of physical prototyping needed.
Now, another reality of aerospace,
Yeah,
deadlines. These projects often have tight schedules.
very much so. Time pressure is common.
So how do they manage that? Our expert mentioned project management tools like MS Project
Yeah, breaking down massive goals into smaller, manageable steps, milestones, tracking progress.
and communication again. Seems crucial.
Absolutely critical. Keeping everyone on the team informed, coordinating efforts, anticipating potential delays. It's skill in itself, managing time and teamwork in such a complex environment.
Okay, let's shift gears slightly. Propulsion. What makes these things go?
Engines, a core part of aerospace, obviously.
Our interviewee had experience analyzing small turbojet engines, the kind you'd find on, say, smaller aircraft or maybe larger drones.
Right. And the analysis involves looking at key metrics. Fuel efficiency is a big one. How much thrust you get for the fuel burned.
Temperature profiles, too,
Yeah.
inside the engine.
Yep, making sure it doesn't overheat. And measuring the thrust itself, the actual forward force.
So it's about balancing power, efficiency, and operating safely within limits.
Exactly. And optimizing those factors requires a deep understanding of things like thermodynamics, fluid mechanics, materials. It's a very specialized area with constant innovation.
Another area of innovation is materials, right?
Yeah.
Especially composites,
Oh, yes, composite materials have been revolutionary.
like carbon fiber. The big advantage is being strong but light.
That's the key. Excellent strength-to-weight ratio. Massively important when every ounce matters for fuel efficiency and performance.
Our technologists had experience modeling these materials in software
Yeah.
and comparing them.
Yes, comparing how composites perform under stress versus traditional metals like aluminum. Understanding their behavior is critical for designing with them effectively.
It sounds like they allow for designs that just weren't possible before.
In many ways, yes. More aerodynamic shapes, lighter structures, better overall efficiency. Composites are a game changer.
Now, in a field where tiny errors can matter so much, data accuracy must be, well, vital.
Paramount. Absolutely critical. There's zero room for error in the data used for design, analysis, or reporting.
So how do they ensure that accuracy? Our expert mentioned things like double-checking systems.
Rigorous checks. Using automated calculations in software like Excel or MATLAB helps minimize manual input errors.
And peer reviews, having colleagues check the work.
Yes. Getting another set of eyes on the data, on the calculations, before anything is finalized. It's standard practice.
Because the consequences of bad data could be significant.
Catastrophic, potentially. When you're dealing with flight safety and incredibly expensive hardware, data integrity is non-negotiable.
It's cool to hear about direct contributions too, not just analysis, but actual design work.
Yeah, our technologist mentioned working on a modular drone system for surveillance.
Modular meaning you could swap parts easily.
Something like that. And their specific contribution was the landing gear.
Designing the landing gear. Seems specific, but important.
Very important. The goals were clear. Make it lightweight, but also really good at absorbing the shock of landing. You need to protect the drone and its expensive sensors.
So even a subsystem like landing gear requires specialized design focus.
Absolutely. Every component plays a role. Optimizing that gear directly impacts the drone's usability and reliability.
Okay, another real-world challenge. Conflicting priorities. In big projects, different people, different teams might have different urgent needs.
Happens all the time. Budget versus schedule versus performance versus safety features. Sometimes these conflict.
So how do you navigate that? Our interviewee talked about assessing the impact of each demand.
Understanding the consequences, and then communication. Talking openly with team leaders, stakeholders, understanding their perspectives.
And trying to find a balanced way forward, addressing the most critical things.
Exactly. Proposing a solution, documenting the decision and the reasoning behind it. Clear communication and documentation are key to resolving those conflicts productively.
Looking ahead now, sustainability. That seems to be a growing focus everywhere, including aerospace.
A huge focus, and a necessary one.
Our technologists mentioned lighter materials, which we've touched on, but also exploring electric propulsion.
Yes, reducing reliance on fossil fuels is a major goal. Electric and hybrid electric systems are getting a lot of research attention.
And just designing for overall efficiency, minimizing environmental impact.
Right. Aerodynamic improvements, more efficient engines, better flight routing. It all contributes. Our interviewee even mentioned a personal passion for this green aviation movement.
It feels like the future of flight has to be more sustainable.
It does. It's about technological advancement, yes, but also environmental responsibility, ensuring the long-term viability of air travel and space exploration.
And finally, wrapping it all together, our expert really stressed that aerospace is fundamentally a team sport.
Absolutely. Collaboration is everything.
Technical skills are the foundation, of course.
Mm.
You need to know your stuff.
But being able to work effectively with others, people from different disciplines, different backgrounds, that's just as important.
And being open to feedback, constructive criticism.
Crucial, especially in a field focused on safety and continuous improvement. You need to be able to share knowledge, learn from others, and work towards that common goal together.
So as we wrap up this deep dive, pulling from that technologist's insights, it really paints a picture of an incredibly multifaceted field.
It really does. From that initial spark, that childhood dream.
Through the intense design work with tools like CAD, the vital aerodynamics, the methodical troubleshooting,
The rigorous testing, the constant focus on safety and regulations.
managing complex projects, developing new materials and propulsion, ensuring data is perfect.
And now, this increasing drive for sustainability. It demands so much. Technical skill, yes, but also that collaborative spirit.
Yeah, it's dynamic, constantly evolving, driven by pushing boundaries,
Yeah.
but always, always anchored by safety and efficiency. It's a fascinating glimpse into how these incredible machines get made.
And the vital role technologists play in shaping that future.
Which brings us to a final thought for you to ponder. We've talked about the rapid pace of change, the innovations happening now.
Composites, simulation, sustainability focus.
So what might be the next big thing, the truly revolutionary innovation that fundamentally changes how we think about flying or traveling in space?
That's the exciting question, isn't it? What's just over the horizon?
Definitely something to think about. Thanks for joining us for this deep dive into aerospace technology.